welcome to Unit 2, and what we're going to be doing now is we're going to look at classification of matter. So the first thing we want to think about here is the definition for matter. And we describe matter as anything that takes up space and has mass. So in other words, volume and mass is what that would be. There are many different ways that we can classify matter or break this down. First thing I'm going to do is break it down into either being a pure substance or being a mixture, which we'll see comes after this. If it's a pure substance, that means that it can be one of two things. It can either be an element or it can be a compound. And so with elements are just going to be those things that you find on the periodic table. They are composed of one single type of atom. So for example, and this might be hard for those sitting in the room to see this, but this says C for carbon or Al for aluminum. You find that on the periodic table, those are elements. And the smallest possible unit is really the element. The only thing that you can break it down into further is an atom of that same element that has those properties. Now, when you see something like this, where you've got two hydrogens that are bonded together, the way that would be written is H2. Or two oxygens that are bonded together, O2. Those are still considered elements because they are of the same type of atom. They're that single type of atom. So I bring that up because when we come down here to compound, notice that with compounds, we're talking about substances that are composed of two or more different types of elements. So O2, oxygen, is considered an element, not a compound. And as far as compounds go, they can only be separated by chemical means, not by physical means, but by chemical means. And we did a couple demonstrations about this type of stuff so you guys can relate back to that and think about what we did there. But they can be separated by chemical means. The other thing about this, well, I'll wait till we get to the flow chart. Okay, some examples that we also see is that we can break compounds down into inorganic and organic compounds. We really start getting into this more in like Unit 7 when we are trying to really name and write the formulas for those things. But at this point, we just know that an organic compound contains carbon is really all you need to know there. Okay, so whipping through this outline. Then, if it's not a pure substance, being an element or compound, it would be a mixture. And mixtures, remember, just contain two or more different types of substances, and they're not in definite chemical ratios. They're in any proportion whatsoever. So this glass that I've got right here, I see some clear liquid in there. Who knows? Maybe I'm drinking salt water, right? Maybe there's a teaspoon of salt in here and a cup of water. You wouldn't really know it just by looking at it, which means, do you think it's homogeneous or heterogeneous? What would it be? It would be homo, because homo means the same. So it all looks the same. If this were salt water, you can't really sit there and point out the differences between the salt and the water. It looks the same to the naked eye. It's not salt water because that would be gross for me to drink. But any sort of mixture that looks the same, in other words, there's only one phase, everything about it looks the same to the naked eye, that's considered a homogeneous mixture. And a vocab term that you should know is solution. If I use the word solution, I am talking about a homogeneous mixture. So that's just a vocabulary word you should know. Examples. I'm going to put down my microphone for just a second and capture this air in my hand. Ready? Okay. So here I have this sample of air. Everybody see it? So I've got this air in my hand. Is it a heterogeneous or homogeneous mixture? Homogeneous mixture. All gas mixtures are always going to be homogeneous. You're never going to be able to point out that, oh, there's some nitrogen, there's some carbon dioxide, some water vapor, a little bit of oxygen. So you won't ever be able to point out those little pieces and parts. So our example that we just looked at was air. And you can see some other examples as well. Regardless of whether it's, actually let's just say for homogeneous mixtures, we're talking about solutions. So we can also break those down even further and say that solutions can be broken down into solutes and solvents. Which one of those words is bigger? Solvent. It's always going to be in larger amounts, and it does the dissolving. whereas solutes are going to be in smaller amount, and they're what's being dissolved. So in this example that we have here, this is making the good stuff, the good hot chocolate, where you've got the real chocolate right here, which is your solute, and milk, which is your solvent, and together it creates this solution of your chocolate milk. If it's not a homogeneous mixture, then that means it's a heterogeneous mixture, if it's a mixture. And in this case, it's going to be composed of more than one phase. Now, that's kind of a little bit deceptive. It could be two solid phases, but you can see an interface boundary between them. So I should have grabbed my chunk of granite from back there, which I did not. But picture a chunk of granite. Everybody's seen granite, the rock. So you might have this pink plagioclase feldspar that you can see, and ooh, there's the black biotite, which is a mica, and there's some clear quartz, right? So you've got these different pieces and parts that you can point out. So that would be considered a heterogeneous mixture. Now, if we go back to that example of granite, if I told you that quartz, there is a chemical formula for quartz, it's SiO2. So if I told you that, how would you classify quartz? As a compound. It's got a definite chemical formula to it, so it is a compound. It's not up there on the periodic table. You don't see quartz up there, but you would see Si, which is silicon, and you'd see O's, which is oxygen. Okay, so that's for our mixtures. The other part about mixtures is that we can separate them very easily, and we can separate mixtures by physical means. Remember that with compounds, we said that they can only be separated by chemical means. Right here is where we've got that. But with mixtures, you can use physical means. So some physical means that we've got are listed here. Oops. You've got this on your sheet. I'm going to go ahead and flip to this slide right here where it maybe shows it a little bit differently. I think the first one on your outline is distillation. So if you think about the word distillation, there's probably a substance you've heard that used with, a distillery. What substance do you think of? What is it? Maybe water. What's something else? Alcohol. Alcohol is distilled. And typically what happens here, if I were to take a mixture, I take some water and I take some alcohol and I throw them together into a flask. If I want to separate them, I can do it by physical means, and I can do it through the process of distillation. So the point here is that those two liquids, what do you think is different about those two liquids? How could we separate them based on their different, they do have different densities. That might be hard though to do it that way. They're two liquids. What could you do? What else do they have that's different? Boiling points. So you guys know just from even using like isopropyl alcohol or something, you put a little bit on your skin, feels really cool because it evaporates really quickly. So it has a really low boiling point. You don't have to heat it up very high. It turns into a gas. So alcohol has a very low boiling point. When you add a little bit of heat here, that alcohol is going to turn into a gas. It's going to come down this gas tube and condense over here, and you're going to be able to collect your alcohol in this chamber. Meanwhile, this is not heated up to your 100 degrees Celsius, so your water is going to stay water. It is not going to boil off, but your alcohol will. So that's how you can go through a distillation process, separating two liquids based on the fact that they have different boiling points. Okay. Next one I think you have on your list is crystallization or evaporation. You guys have all done this or seen this happen at some point. Kind of the same properties in some respects. You're thinking about something boiling off, but how is this different? It's not two liquids, but you've also got a solid in there. So if you took some salt water and just even put it in the window or heated it up or whatever, your water would evaporate or boil off, and you would be left with your sodium chloride, your salt crystals there. Here's a little example. You can't see this at home, but a little example of making some rock candy. And this was just making a really saturated sugar water solution. And then I had a string that was kind of whipped down into the beaker. But you can see all the crystals that form. So that's just rock candy. All that is sugar, evaporated all of the the water from that solution that I have. Okay, and then next one I think is filtering. That's on your list, and all you're doing there is looking at different particle size. Some of those particles are going to go through the filter paper and some are not, and we call that the filtrate that goes through. Then there was decanting, which is just a nice sciencey word for pouring off. And typically, decanting is used hand in hand with centrifuging. So centrifuging, what you're doing is you're taking some test tubes, putting them in a centrifuge that spins around really quickly, and based on that, you're going to get some separation of some things based on different densities. So these substances have different densities, so you'll get these layers. Or if you have a solid, the solid will go to the bottom, and then you'll have a liquid on top, and that's when you just decant the liquids. You just pour it off. And then another one, I think it's in Unit 7 that we're going to look at this, is chromatography, and that's a pretty cool one. It's where you've got different solutes travel at different speeds based upon their what they're made of. So these pure substances travel at different speeds up this filter paper when it's wicked up there when it's thrown into the solvent. So we'll do a lab on that. Okay, so everything we've talked about so far is a physical means of separation. We have not said anything about these two. So we've got heating, and by heating, yeah, you can heat some things up to have a physical process take place, but if you heat it up enough, you can get a chemical process to take place. And so that's what that's showing. And then electrolysis, running a current through it, you can even separate things like water can be separated into hydrogen and oxygen. Okay, so that's what we've got for separation. Now we move into looking at properties and changes of both physical and chemical properties and changes. And for whatever reason, sorry, these should not be separated like that. They're all the same. Didn't mean to indent parts. So if we start looking at just physical, that's this first part. First thing I want to do is look at the physical properties. As I mentioned when I did that little demo, you can have extensive and intensive physical properties. All a physical property does is describe the substance. We can describe how much of that substance you've got, in which case it's extensive. It's really not telling you a lot about it. If I have 8.3 grams, well, I could have 8.3 grams of anything for the most part. So that's not very descriptive, but that is a physical property. We use this type of information, these extensive physical properties, when we're doing a lot of calculations in lab. More importantly, we look at a lot of intensive physical properties. And these don't depend upon how much matter you have. It doesn't depend upon the amount, just the substance itself. So it doesn't matter how much of it you have, the color is always going to be the same. We can talk about density, freezing or melting points, boiling points, that sort of thing. Malleability, what's that? Good. So how it's hammered into sheets. Metals are pretty malleable. Ductility, how is that different? Pulled into wires. Good. And then conductivity, how that it conducts electricity. Now with all of this information, the ones that are commonly missed are this. When it says changes in state, that's the same thing as saying a phase change, same exact thing. So if I take solid H2O and I put it on my stovetop, I give it some heat and it turns into liquid H2O, and I give it some more heat and it turns into gaseous H2O. It is still H2O. So all that is a physical change. I haven't changed what it is. It's H2O. I've just changed it from being ice to liquid to steam. That one is commonly missed, as is dissolving. If you see this written as a property, it's often written as solubility. So the solubility is a physical property. If something's dissolving, it is just a physical change. It can get back to being what it was, so it's just a physical change. Okay, this is just a quick reminder. Don't make this mistake. If it's a phase change, it's purely a physical change. And then we move on into chemical changes. If a chemical change takes place, you get a new substance formed. It's going to be completely different. And really what you're looking at is how this one substance reacts with other things. So some things that we're going to be looking at, some examples of chemical changes. If it ever says reacts with, that's going to be a chemical change. Corrosion, flammability, combustibility, things like that. And then we've got some things to help us identify chemical changes. You guys have seen every single one of these. The first one, in our first lab that we've done so far, we saw a color change, right? Even more than just seeing a color change, we happen to even see formation of precipitates. Even though you didn't realize a solid, you might not have realized a solid was being formed, we got this yellow. We saw a lot of cloudy, milky colors, and that's because those clear substances came together and a precipitate, a solid, was formed. Itty bitty tiny little specks that made that whole solution look cloudy. We had some gas formation just in that demo I just did when we took the zinc and the hydrochloric acid. So we got the gas bubbles and we had that hydrogen gas. We saw some energy changes. It heated up that flask. So all of these are going to be indicators of chemical changes. Okay, now we move on into a flow chart. And you've got this on your paper as well. It's on the back side. There is more than one way to create this flow chart. Your outline does it in one direction, and this is in a different direction. So I don't want you to get hung up on which direction to make a flow chart, because I'm not going to ask you to repeat it. But just to give you an idea that this is another way to organize it. I can take all of matter, and I can break it down into either being that it looks different to the naked eye, or it looks the same to the naked eye. So that's one way of breaking it down. If it looks different, what is the only possibility? How do you have to classify it? Mixture. And yeah, you can have a homogeneous mixture. That's also possible. So you can have that part of your chart. But if it's a pure substance, then it's either going to be an element or a compound. Okay, so for those at home, you guys are going to be able to fill this in and just pause and do whatever you want. For those that are here in class today, we are not going to have time to fill this all in, but it's okay because you have this in your notes already. I'm going to highlight the ones that I want you to kind of mark down. So the first thing, we've already said that heterogeneous, I said that you can see different parts to the naked eye. So in other words, parts are not evenly distributed, and homogeneous, they are evenly distributed. So we already know that part. We know this stuff about the mixture. This is in our outline that we already went through, so I'm going to go through it really quickly. You have two or more substances that are physically combined, meaning that you can physically separate them. They can be, and then here's the part that I'm going to come back to. I'm going to come back to that. Then we come over here to our pure substances. In our pure substances, you can have elements or compounds. So remember, your elements, they cannot be chemically changed or broken down. The atom is the smallest particle of that element to still retain those properties, which is what we have listed there. Whereas compounds, let's see where we can put this. Compounds, they are a chemical combination of two or more elements, so we know that. And they cannot be separated by physical means. They can only be separated by chemical means. Now, these are the two things that we're going to make a note of. If I go back here to my mixture, earlier I was pretending to drink salt water. So here in my glass right here, I've got some salt and I got some water, right? Well, when I mix them together, what do I get? Salty water. In other words, as a mixture, they are retaining their original properties. So an example would be salt water. Also remember, we said it can be in any ratio. There's no formula that salt water has to be this amount, that salt has to be this amount and water has to be this much. So any ratio. But the key is it retains its original properties. If I run over here now to compounds, let's think about this. Let's look at our salt example that I mentioned in my cup. I go back to elements. Salt is just sodium chloride. Sodium, you might not normally think about it, but we're looking at a periodic table right now. It's in that first column. It is a metal. And not only is it a metal, it is a really reactive metal. You throw it in water, it explodes for the most part. It is a highly reactive metal, so that's sodium. Chlorine. There's a name for this type of gas that was used in the war. What was it called? Mustard gas. So we have this really reactive metal, and we have this poisonous gas that can kill you. So what do we do with this stuff? Exactly. Chemically bonded, it forms that sodium chloride. We throw it in our French fries, and we eat it. So example would be sodium chloride. It just didn't show up on the screen here. So sodium chloride has completely different properties than the elements that create it. And that's a big part of this, of what I want you guys to see. Properties are different from the properties of those individual elements. Okay? How do you guys feel with this stuff? Good? All right, so I'm going to keep going. I'm going to whip past this. And I just want to show you, we said that the flow chart can be in a different form. Here's another way that it could be represented. This is how it's represented in your outline, that it starts off as matter, and then it goes to being a pure substance or a mixture. And those pure substances are elements and compounds. Mixtures can either be homogeneous or heterogeneous. Do not get hung up on which way to break it down. It's all telling you exactly the same stuff. Pure substances can be, or all of these guys right here are pure substances. And they're all homogeneous, yeah. Okay, so now we are looking at our papers. On the same side of your paper, for my classes anyway, as your matter flow chart, you have a little table. Mine just looks different. I threw in some pictures. But yours starts off, it says matter, substances versus mixtures. And by substances, we're talking about pure substances. So I am going to not just break it down into substance and mixture, I'm going to break it down into a substance of compound or element and hetero or homogeneous mixture is how we're breaking this down. So the first one on your sheet says chlorine. So think about that one, how you would classify chlorine. And I've got them down here. They're not showing up. So chlorine, how do you want to classify that? It is a pure substance. What type of pure substance? Element. It is an element. It is over there on the periodic table. Chlorine is an element. Next one we have is water. How do you want to classify that? Hey, is there a formula for it? Yes, there is, and I just heard compound. So the formula is H2O. So that's got to be a compound. Okay, next one is soil. Look at this soil. I see an earthworm, a rock. I don't know, not really, but pretend I do. There's some soil and grass. So how do you want to classify that? In what type of mixture? Hetero, because you can see those different pieces and parts. Okay, sugar water. I don't like my example here. Pretend it just looks like clear water. Ignore the little lemon that you see. If it's just clear looking, it would be homogeneous mixture. Oxygen, element. And carbon dioxide. And Rocky Road ice cream. That is heterogeneous because there's some nuts and marshmallows and chocolatey goodness. Alcohol. Now here lies the problem. This is first year chemistry. You guys really don't have enough experience to know some of these things. Some people might think, I don't know, is alcohol on the periodic table? Do you think it is? No, it's not. There is a chemical formula for it. There's more than one type of alcohol, but if we were more specific and told you which type it would have a chemical formula that has some carbons, hydrogens, and oxygens in it. So it has a chemical formula. So therefore, you're going to classify it as a compound. And pure air, in other words, none of that Los Angeles stuff. It is homogeneous because all gas mixtures are homogeneous. All gas mixtures are homogeneous. Last one, iron. Elements on the periodic table. Okay, nice job. So we are done with that one sheet. We have another sheet. We're moving on into some properties and changes. So the first one we're going to look at is talking about properties. It's either going to be a physical or a chemical property. So we're going to go down this pretty quickly so that we have time for the fun stuff at the end. Blue color, if it's blue, what would you call that? Physical, density. Physical, flammability. Yes, solubility. Physical, awesome. Do not make that mistake and call it chemical later on. So reacts with blah, blah, blah. Chemical, I don't even care what it's reacting with. It says it's reacting with something. So that's going to be a chemical change. Supports combustion. Chemical. Sour. Physical. Melting point. Physical. Reacts with. Reacts with. So you might want to read through and just see what those things are, what types of chemical reactions might take place, but that whole reacts with is the giveaway. Hardness. Boiling point. Can neutralize a base. Chemical. Luster, that's shininess. Physical. And odor. Okay, awesome. Then we move on into thinking about those actual changes, not just the properties. So first one, sodium hydroxide dissolves in water. Physical. Hydrochloric acid reacts with potassium hydroxide to produce salt water and heat. Chemical. Pellet of sodium is sliced in two. Physical. Water is heated and changed to steam. Physical. Potassium chlorate decomposes to be potassium chloride and oxygen. Chemical. You can see a reaction's going on. Iron rusts. Chemical because it's reacting with the oxygen in the air. Okay, so H2O, sodium pellet, catches fire, hydrogen gas, all this stuff. Chemical. Evaporation. Ice melting. Milk sours. Chemical. I've got this huge phobia towards rotten dairy products, and this just sounds so nasty to me. You guys know that a chemical process has taken place. It's a very different substance than when it first started, right? So that's a chemical. Okay, sugar dissolves in water. Physical. Wood rotting. Pancakes cooking on a griddle. Chemical, because you're never going to get that egg back. It's never going to be the same. It's you're giving it enough heat to actually cause some bonds to break and new bonds to form. Okay, what do you think about grass growing in a lawn? It's chemical. Think about photosynthesis. Think about what you learned in biology last year. This is probably a really good point to bring up the fact that I know we're writing chemical and physical, but every single one of these has a physical change taking place. It's just that only the chemicals have chemical changes as well. But all of those chemical changes are also accompanied by physical changes, right? You can look at that and think, yeah, the grass is getting longer. That's the physical change that you're seeing. But it's a chemical process that's taking place in that. Okay, then we have a tire is inflated with air. And then the next one is food is digested. Chemical. And last one, which we can't see on here, but it says water is absorbed by a paper towel. Physical. Okay, we are moving on to the fun stuff now. And we are going to, in this case, let me just let you guys know that you will see this again. You will see it on a quiz. You will see it on a test. You should be able to identify these things on an atomic level. So what we're doing in this situation is we're pretending that we're taking these samples and blowing them up gajillions of times, and they're contained in some sort of enclosed container, a beaker or something with a lid. So we are looking at these and trying to classify them based on these three categories. I'm going to start with letter E. Let's start with letter E right here. So the first one, our first category, remember this is on an atomic level, so we're trying to represent these molecules and atoms on an atomic level. Do you want to classify this as being a homogeneous mixture A heterogeneous mixture or a pure substance? I'm going with pure substance. They all look the same, right? So that is a pure substance. In fact, that Mickey Mouse kind of look, what do you think the substance is, possibly? Water, because you've got that 2 parts hydrogen for every 1 part oxygen. So that's the look of water. So this is a pure substance because they're all the same. Would you categorize that as being all the same elements, compounds, or they're both things in it? They're compounds. And here's the hard thing to represent in this type of drawing, but tell me what you think it's not. Which phase is this not? It is not a gas because gases fill the containers that they're in. Based on this, you know, this is a tough call. They are all oriented the same direction. You know, you could call it a liquid or a solid. If it's a solid, it's a very crystalline pattern. If it's a liquid, it's kind of a little more flowy, but down at the bottom. I don't really care on this. We're going to say a liquid or a solid on that one, because you really can't tell too well. Okay, so we are now going to jump to this. And this was like years ago when we got smart boards. This was the very first activity that I created with a smart board, so brings back some fond memories for me. But this first one, now we're looking at A. Do you want to classify this as a homogeneous mixture, heterogeneous mixture, or pure substance? Pure substance. There we go. And do you want to call it a pure substance as an element, a compound, or both? It is an element because it's just those single circles, just like an atom, right? And then, what do you want to call it? Solid, liquid, gas, or both? Gas, because it is filling up that container that it's in. Okay, okay, next one. Here we have, what do you want to say? Heterogeneous, good, because you're looking at that, you know it's a mixture. You see 2 different things. And when you look at that, you see that you got something down on the bottom of the beaker, and you got some other stuff floating near the top. So that's heterogeneous. And do you want to call it element, compound, or both? Both, good. Because these guys are compounds up here. This is an element down here. Remember, it has to be different atoms, different types of elements for it to be classified as a compound. So in this case, we've got both. And then finally, what about our phases? Combination. I would say you've got some gas and probably liquid down there. Okay. Next one. What do you think? I heard both. Hetero and homo. Which one? Homo. Why do you think it's homo? Because it's a gas. It's a gas. So we answered the last one, but because it's a gas, it has to be considered a homogeneous mixture. You can't, in this air, there's no way we can break apart the nitrogen from the carbon dioxide just by looking at this gaseous mixture that's surrounding us. So next one, what do you want to call it? It's elements, right? It's a homogeneous mixture of elements. And we've already ruined the surprise on the last one that it is a gas. And last one. Okay. What do you want to call this one? Is it a mixture or pure substance? It's pure. It is pure because every single one of those guys looks the same. So it's a pure substance. And is it a pure substance composed of elements or compounds? Compounds. And how do you want to phrase that? Let's call it a liquid because it doesn't look that crystalline to me, that nice pattern look. Okay, so I am going to give answers to the rest of them here in class, and at home you just need to make sure you get those from someone. That's it.